Good day, everyone. My name is Rutvik Shah, and this is my CS 499 Honors Seminar presentation for the topic of Assuring Security through Cryptography and Digital Signatures. This presentation aims to explain cryptographic methods of digital signatures and certifications. We start with introducing the need for security and what is it that we want to secure. We then move on to learning the concept of cryptography and its importance in security techniques in practice. We then talk about the types of cryptographic methods. After that, we expand in depth about the public key or asymmetric key cryptography methods. In doing so, we learn in the process and applications of digital signatures and certifications that we see being used in a lot of modern day digital communications. We then talk about various concerns and the importance of working in this field before we end the presentation. Sounds good? Let's move on. So, why is there even a need for security? In an ideal world, everyone would respect each other's privacy and malicious practices would be non existent. Sadly, we do not live in such a world. Even in our day to day lives, when we want to talk about something sensitive, we don't go on broadcasting it for everyone to hear. We talk about it in private with the person we want to talk to. We are sure the things that we talk about are done so in a safe space. This is the same concept we are trying to apply while going digital. So, then what is it that we want to secure? In this modern era, everything is interconnected. So, in this Internet of Things, there is a tremendous amount of message and file exchanges happening at every time. There could be some malicious messages added in such a system that can disrupt everything and destroy it in a matter of seconds. These situations are precisely what we want to prevent, and we should focus more on securing these systems that handle sensitive information exchanges. So, how do we approach security? Let's find out. Cryptography. Now, cryptography is a method or approach which we use to secure communications between systems. The word cryptography can be broken down as the study of hidden meanings in seemingly plain set of words. Now we apply this concept to messages and information that is being exchanged between two systems. We can break the process of cryptography into three major parts. Encryption. As a sender, we have some sort of message that we want to send, but we also want to make sure that no one can tamper with the message and it reaches safely to its destination. Thus, we convert our meaningful message into something that is unreadable and doesn't make any sense at all to others. Ciphertext. The unreadable data that we converted from our message that we meant to send is called ciphertext. Decryption. Now, let us think from the receiver's perspective. Let us say the receiver gets the ciphertext. How can it make sense of it? Simply speaking, it can't, unless it has some instructions on how to transform the ciphertext back into the meaningful message. This process is called decryption. Once decrypted, the receiver can now see what the sender meant to send in the first place. This whole system, when put together, is a naive example of a successful secure communication between two systems. Now let us learn about types of cryptography. But before we do, it is imperative to know the basic process of encrypting and decrypting data. When we change regular text to ciphertext, we do something to it so that it makes no sense to others. How? How do we encrypt it like that? This is where the concept of keys come in. When we encrypt, We change the message into another message which doesn't make any sense in itself using something called a key. A key is what decides how we change the regular text into the ciphertext and vice versa. For example, I have a key that changes the letter A to the number 5. Now I want to send a message that is ALICE. My ciphertext after encryption would be 5LICE. Now I send it to receiver. Now as a receiver, I wouldn't know what 5LICE means unless I have a key to decrypt it. Let us say I do have a key to decrypt it, and upon decryption, I know that I have to replace 5 with A. So I replace 5LICE with ALICE, and I can say that the message that I received is ALICE, which is what we wanted to send in the first place. Okay, now we can talk about types of cryptography. We can divide cryptography into broadly two types or two methods. The first is the symmetric key approach. This is when the sender and the receiver have the same key to work with. In this approach, we have just one key. It is a secret key that only the sender and the receiver know about. The sender encrypts the message using the secret key and sends it. The receiver can decrypt using the same secret key it has. If the secret key was not same, then the message that was decrypted or that couldn't be decrypted is invalid and is not authenticated. If the keys were same, then the message is authenticated and valid. Some examples are the Advanced Encryption Standard AES, the Data Encryption Standard DES, and more. We will not discuss more about this since it is out of scope for our presentation. We want to focus on signatures and certificates. So now let us move on to explain asymmetric key methods. They are methods in which public keys are utilized to encode while private keys can decode. Okay, it is relatively newer than the symmetric key cryptography methods. As mentioned, we have two sets of keys present, public key and private key. Public key is a freely available key to encrypt messages that can be sent to target system. And private key is only known to the target and no one else. Messages containing the public key can be decrypted by this private key as a pair. This process can happen to and fro. So messages encrypted using private keys can be decrypted using public keys as well. In this approach, we use the public key to encrypt the message meant for the receiver. The receiver then receives this encrypted message, which can only be decrypted by the secret, private key of the receiver. If someone other than the receiver is trying to decrypt this, then he or she wouldn't know the private key and as a result wouldn't be able to decrypt the message back into its original form. This is particularly interesting since we only need to make sure that the decryption or the private key is kept secure. Our public key can be given out freely. We can get messages from anyone that has access to our public key, but no one can decrypt those messages except us because we have access to our private key. For example, if we want to send something from system A to system B, we encrypt the message using system B's public key and we decrypt the message using system B's private key, which is known only to B. The same can be true when we want to send the message for A. Alright, now that we know the basic idea of interaction with public key cryptography, we can move on to learn about digital signatures and certificates. Digital signatures. So what are digital signatures? Well, to put it simply, they are just a digital version of signatures. As we know, we use signatures as a tool of authenticity in real life. When we sign and agree to something, it makes that thing official and legally binding to us. This is the same concept we visualize while going digital with signatures. They are a way to authenticate identity and integrity of messages received and sent. Let us now learn and break down the process of making and using digital signatures with public key cryptography. Number one, we can create message digest. A message digest is nothing but a single string of digits derived from the message that is to be sent. Now, how do we convert the message to this string? We send the message into some sort of hashing function which produces as an output the digit of strings, the string of digits. Number two, we can now create a digital signature by encrypting the message digest with our private key. We can then send this digital signature along with the original message to the receiver. Now, the receiver can decrypt the signature using the public key and extract the digest from the sender. The receiver, on the other hand, also creates its own digest using the message it received along with the signature. Now the receiver compares both the digests. If they both match, then the message received is valid and it was not tampered with. If they don't match, we know that the message is invalid because it has been tampered with and we can take appropriate actions thus. Let us now look at an intuitive example to better understand this whole process of exchange of messages with digital signature validation. Okay, let us now visualize digital signature process. Let us assume that we have a sender S and a receiver R. Now, S wants to send a message M, which is hello, to our receiver R. So S has to convert the message M into a message digest as follows. The message M is sent to a hash function H, which gives an output 19226 in our case. So now we have the message digest MD as 19226. Now the sender S can encrypt this message digest with its private key. This is our digital signature DS. Sending now we can see that the sender S sends the digital signature and the message M to our receiver R. Now the receiver R receives the digital signature and the message. It does two things. Number one, from the message that it received, it creates its own message digest using the hash function and stores it. Number two, from the digital signature received, it decrypts that digital signature using the public key of the sender. Now it has two sets of message digests, one from the sender and one that it created. Now the receiver checks if the message digest from sender is equal to the message digest that the receiver created. If that is the case, then we know that the message M is untampered and authenticated. If not, we know that the message M is tampered. Let us now look at two examples of this. Let us say that the receiver R received a message M which was bye, but the sender sent the message M which was hello. So we can see that the message digest that the receiver created was 879 and the message digest that it decrypted was 19226. Since both of those are not same, the receiver R instantly knows that the message M has been tampered with and is not authenticated. So we can now take actions. Case 2. Let us say that the message M was hello and the message received by the receiver was also hello. So the receiver creates a message digest which is 19226 and the receiver also decrypts a message digest from the signature which came out to be 19226. Now that we compare the message digest from receiver and from the sender we can see that they are both equal. So we can say that M, which is hello, is what the sender actually sent and it has not been touched or tampered with. So this is a valid scenario. Now that we have learned about digital signatures through this example, we are ready to move on to learn about digital certificates. So let us now learn about digital certificates. Let us say that we don't exactly trust the process of digital signature validation. It is just not enough to give our entire trust to the other system. Well, we make use of something called the digital certificates as an additional layer of trust. Digital certificates are certificates telling that the entity is trustworthy. It has the public key inside the certificate along with other identification information which may or may not be used. So, how can we trust a digital certificate? Well, digital certificates are issued by a reputed third party, and the process of acquiring a certificate in itself has to go through digital signature process. So this adds an extra layer of authentication, which makes us deepen our trust with the other party. Okay, so let us now visualize how conversations between two systems start using the digital certificates. Since user A wants to send a message, it asks the certification from user B. Once A receives B's certificate, it verifies the authenticity with the third party certification authority. This happens with a signature exchange, which in itself is quite secure. Now, once A is sure that B's certificate is valid, A can trust B. This same process happens with B to A as well. So now A and B both have validated each other's certificates and are trusting each other, with the certification authority CA as a middleman or third party. Now A can proceed to sending messages to B using the digital signature scheme in the example we described before, and user B can also do the same with receiving and sending. This whole process can happen to and fro as many times as we want. Now, as we can understand, this process is just another layer of verification. It is to be extra sure that the sender or the receiver is actually who he or she claims to be. Some of the common algorithms making use of these public key cryptographic methods are the RSA, DSA, the SHA implementations of RSA and DSA, and much more. All right, now that we understand the approach and in practice mechanisms of assuring security through digital signatures and certifications, it is imperative that we talk about the concerns and importance of working in this field. Think about the advancements happening in quantum computing. Once we have a large enough computer that can be deployed for public use, which may not be as soon as a year or two, but after 10 years or so, this might be the new standard. As we know, quantum computers can store both zeros and ones in just one single unit. So they can calculate things at an exponentially faster rate than the current speed norms. So a brute force attack that would be practically impossible today with our current computers could very well be feasible when using quantum computers to do so. Now, what if you are developing security system that works with very sensitive data? As we know, even the tiniest bit of errors or negligence on your part can be and will be exploited. This whole system can crumble everything in just a matter of seconds. This is exactly why, if there will be people that are ready to exploit, then there must always be people ready to safeguard. This is the burden and the importance that you must understand that you take on when you start working in a field like this. Your decisions can and will impact potentially millions of people. This marks the end of our presentation. Thank you for your time, and I hope you have learned something new. All questions, suggestions, and criticisms are welcome.